continuing on with lesson 43, and some of this may not be in your notes, so make sure you do watch this video. And this is based on the last example. It says, in the process of alpha decay, the total mass of the daughter nucleus plus the alpha particle is less than the original parent nucleus. The missing mass isn't really missing. It's been turned into energy following Einstein's formula E equals mc squared. This works out for our new understanding of conservation of mass and conservation of energy being interchangeable. The energy is found mostly in the kinetic energy of the alpha particle and the daughter nucleus moving away from each other. So when an atom decays, they basically move away from each other. Just as when you fire a gun, if you fire a gun to the left, your gun will move to the right. The energy, the alpha particle usually moves faster, since the alpha particle is almost always much lighter than the daughter nucleus. Also keep in mind that if the parent nucleus was at rest, the alpha and the daughter nucleus will travel in opposite directions, so the conservation of momentum is obeyed. Okay, so here's another example of alpha decay, and in this one it says determine how much energy is released when uranium-238 decays to thorium-234. So first of all, you're going to want to write out the decay equation. That's uranium-238. And if you look on your periodic table, you will find out that thorium has an atomic number of 90. Therefore, in order to balance this equation out, we must have a 2 here and a 4 there. So we're clearly talking about alpha decay here. And this will make more sense when we do beta decay, and you have to determine is something alpha decay or is something beta decay, and you'll do that by balancing the equation. So this is alpha decay, and then what you're going to have to do is you're going to have to go into your textbook or another source and find out what the atomic masses of all of these elements are, and I'll just give them to you. Uranium-238 is 238.0508 atomic mass units. The alpha particle is 4.0026 atomic mass units, and thorium is, whoops, right, atomic mass units. Now, if you add the alpha particle and the thorium on the right side, you will see that they do not equal 238.0508. So they don't equal the left side. So you've got this is going to be greater than the combined mass of those, which is going to be and that mass difference is, again, a form of the mass defect. That's what's converted to energy when uranium-238 decays. It releases some energy. You can find out that energy just using E equals mc squared. So we're going to subtract these two values to get the mass defect. That's going to give us 0.0046 atomic mass units. That's the mass that's unaccounted for. Well, the mass defect, if we want to call it that. It doesn't really matter what you call it. It is the mass that is converted to energy. That's the important concept here. And therefore, we can use E equals mc squared to find out how much energy was released. Don't forget to change this into, you got to multiply it by 1.660593 kilograms to get it into kilograms. And then you can plug it into E equals mc squared. And that turns out to be 6.87 times 10 to the negative 13 joules, which we again, we like to express this in electron volts or mega electron volts. So let's change that to electron volts, and that's going to equal 4.30 times 10 to the 6 electron volts. And that one works out nicely because since it's times 10 to the 6, we don't even need to change anything. We can just express that as 4.30 mega electron volts. All right, that's how much energy is released when one uranium atom, uranium-238, decays into a thorium atom. So it's a lot of energy for one single atom. Okay, I think we'll move right on to beta decay here. Beta decay. So beta decay is very interesting because it's going to explain a lot of things. One of them of which is why we said in an earlier lesson that the mass of the neutron is slightly bigger than the mass of the proton. It brings up other questions that I don't know the answers to, but it does explain that fact. It says beta negative decay happens during a process that at first seems crazy. A neutron falls apart and becomes a proton and an electron. So there's your explanation for the mass difference, that a neutron is actually a proton and an electron combined. And so you add the mass of an electron to a proton and you get a neutron. So it says it's not as crazy as it sounds if you look at the facts. Remember earlier when we pointed out okay, I just discussed that. In beta negative decay, the neutron becomes a proton, which stays in the nucleus, and the electron goes flying out as a beta particle. All right, so this is, let's just get some empty space here. This is very different. Let's again go with helium. So that is a helium, and I've got 2 protons and 2 neutrons. And in beta negative, what happens is, let me go back to it, it says go back to here. In beta negative, the neutron becomes a proton. So let's go back down to here. So what's going to happen if one of these neutrons, it ejects a beta particle, which is essentially just an electron, and becomes a proton. So now all of a sudden, what do we have? Well, we have whatever has 3 neutrons. Why didn't I bring my periodic table, and why don't I know that? That's almost embarrassing. Not quite, too old to be embarrassed about much. So whatever has 3 protons, that helium has now become a new element and has ejected a beta particle, which is essentially an electron, because what we're saying here is that the neutron is really a proton and an electron, and if you eject, and notice how that works out very nicely, because that's +1, that's -1, then neutral. If you eject this part of it, all of a sudden it just becomes a proton. So that's what they're saying for beta negative decay. Now there is a little more to it than that. So let's go through, okay, blah, blah. So let's write out a beta negative decay for calcium 46. Calcium 46. Calcium has an atomic number of 20. Okay, and it's going to eject. Now, this is how we depict a beta particle. Write the beta symbol, and down here, this is actually going to be a conservation of charge concept. We're going to put -1. Why are we going to put -1? Because it's 1 electron and it's negatively charged. How many nucleons does an electron have? And the answer is 0. So this is how we depict or represent a beta negative particle. You write the beta symbol, a -1 at the bottom, and a 0 on the top. 0 means there are no nucleons because there are no neutrons and no protons. The -1 means it's just an electron. And what you're going to see here is that the top numbers in this become conservation of nucleons, and the bottom numbers here turn out to be the conservation of charge. Okay, so what do we need to balance out this equation? Well, this is 20 and this is -1. So what has to go here so that I get 20 altogether? 21, because 21 plus -1 is 20. So now the bottom numbers balance out, and I can see that my calcium has now become something else. It's become whatever has 21, which turns out to be scandium. I hope. And yeah, and now let's do the top. The top is 46 and 0, so this will be 46. So now the top balances out because the conservation of nucleons is now obeyed. And therefore, we look on a periodic table, we find out the element with an atomic number of 21 is scandium, and that's our answer. There's only one problem. You go through all this, and what happened, if you read the notes below, it says there's one thing we should put into our reactions for beta negative decay. When physicists first examined beta negative decays, they figured that since the electrons that are the beta particles are so light, they should just go shooting out of the nucleus at tremendous speeds. In reality, they move a lot slower. In order to still have conservation laws obeyed, it was realized that a very small neutral particle must also be emitted from the nucleus. Today, we call that particle an antineutrino, and it has this symbol, a V with a line over it. And so because the reaction, or because the process didn't quite obey the laws of conservation of energy and momentum, they discovered that there must be something else emitted, and that is what we call a neutrino, or an antineutrino in this case. And so we have to add it right there to the answer. So anytime you have beta negative decay, you have to add this antineutrino to the end of the decay. All right, and then look at this. This is really important. A neutron, this is what happens in beta negative decay. A neutron becomes a proton plus a beta particle plus an antineutrino, and everything balances out there. So it's all good. What do we have in addition to beta negative decay? Well, we have beta positive decay. The other type of beta decay we examine is called beta positive. Beta positive is different from beta negative because the particles emitted are the exact opposite. So instead of ejecting an electron, it will eject an anti-electron, which we call a positron. And a positron is very simply an electron that has a positive charge. That's why we also call it an anti-electron. Okay, so a positron has the same mass as an electron, but it is positively charged. And we use the symbol beta with a positive to represent a positive. Now, how is this different from beta negative decay? Well, in beta negative decay, a neutron turned into a proton. In beta positive decay, a proton turns into a neutron. Which is why I say this kind of leaves a question in your head, which says, well, if the neutron has more mass than a proton, then how does this one work? Well, you're gonna have to ask smarter people than me to answer that question. So here we have a proton becoming a neutron. Why? What does it do? Here's a proton, and that proton we're gonna say is made out or has a positive. The positive part of the neutron is called of a proton is called a positron. And if it ejects it, it becomes neutral. So it becomes a neutron. a neutron, and then we have a beta positive particle, and here is a neutrino, not an antineutrino, it's a neutrino. So when you put a line over something, it usually means anti. In this case, it's a neutrino. So let's go through our example here. For beta positive decay, it says potassium is known to go through beta positive decays. Write out an equation. So potassium is 40K19. And it goes through a beta positive decay. So one of the protons in the nucleus of potassium becomes a neutron. And therefore, so the best way to do these often is write out here. If it goes to a beta positive, I'm going to write, whoopsie, why did I write the plus there? There's my beta positive particle. And now we just have to balance it out. If I have a 19 over here and a 1 here, this must be 18. 40 up here, 0 up here, 40. Which element has an atomic number of 18? That happens to be, is it argon? Argon. It is argon. And what do you have to add to the end of all beta positives? A neutrino. So that's the decay equation for positive beta decay for potassium 40. Okay, and then gamma, how are we doing for time here? Oh my gosh. Okay, actually, we're gonna have, this lesson is gonna have to be in 3 parts. So I'll stop there and then we'll talk about gamma radiation.